or MRS.
Yeah, parameterized.
And my parents live there, so it's super cheap.
Why Emerald mentioned
Because I think it's a thing of they probably signed a contract.
If you want to move this, you can also move this into any of the corners. I don't know which corner you prefer to have
We
that.
won't really grow.
But you would just go into,
the
menu. If you wanted just a camera.
Should I point on where is the receiver?
If you want to, there's a receiver in the camera and also in the codec, but if you wanted just the camera, you'll have to do the zoom in and out first real quick, so it knows you wanted a camera. Oh no, you don't.
Maybe APX. I don't think ACX.
It kind of felt the same size.
Yeah, so if you want this in a different corner, you can do that too.
But ACS, like next, I think in August, it's at San Diego again. And then, like, they have like 5 venues that they go to.
There is the east and west and south and south.
Sure. But I think for what I would assume is it's MRS. They probably got a deal saying, oh, we'll be here for the next 6 weeks.
Yeah, basically, do have something like actually do that. It's very unusual.
And
It's same thing
I think
every
Phoenix is relatively expensive to fly,
Okay.
no matter where you go.
Yeah. So this corner's good for the video?
Yes.
Okay, sounds good. Let me know if you need something else.
Thanks for coming, and we do have a special meeting and a special speaker. Aaron is going to provide a research update. You're not sure?
wait.
About. So I was trying to invite more people, telling that it will be interesting things for more general audience. For example, for physics audience, like Dan, I've tried to attract him by telling that there will be something on quasi-particles. So it will be for quasi-particles and particles. Aaron may.
So, yeah, as Dimitri kind of outlined, I'm investigating Polaron formation and perovskite, specifically perovskite quantum dot, which we'll go over in a second why quantum dot compared to other dimensionality structures. And then specifically, we're hoping to find IR emission pathways of these materials are specifically efficient IR pathways. So, just a general table of contents. I'll spend a little bit going over introduction and some literature review of what's been done and motivation behind why we want IR emission in the first place. And then a couple of different methods we plan to use to simulate the efficiency of IR emission from DFT simulations, and then some mostly completed structural and optical properties of the systems I'm looking at, and then some preliminary results on the excited state dynamics. So we're looking for IR emissions. So I didn't, before looking it up, I didn't know that different like regions of IR that people are specifically interested for. And usually it comes down to they partition it between based on device applications. But the most general thing I've seen is if you just look at the IR spectrum of light, you have near IR, which is like around 1 nanometer, up to 1.4, or not micrometer, not nanometer. And then they break it into short IR, mid IR, long IR, and then very far IR. And then usually long IR and far IR are more for like thermal, for like military applications, for like heat seeking, whereas like communications are more short and mid IR. So why do we care about IR emissions? So one thing is wireless communications, so like this device, this IR emitter. So basically, or if you're using, like, if you're at your TV, too lazy to get up and change the channel, you can use your remote to change the channel. So the basic idea is you put, you excite some sort of material and then it emits some light. It's giving a signal, then it's talking to a specific receiver which you want to absorb in the IR range. And then that converts to an output signal. So if you click the dot,
Oh, what are the symbols there? If there is audience deep in radio electronics.
It's been a while since I've went over circuit elements. This looks some sort of like a diode. And another
Can you point like where is the diode
like
units? Just for curiosity, we're not meeting about it, but
right. I think it's
it's too many parts. There are like two.
The triangle with the line below it is the.
it's a diode. I think this is like a rectifier. And this is some sort of junction.
This
Kind of a transistor.
looks like a transistor. So when there are three lines coming
Right.
together,
That's what I meant by junction. Something that, or like a gate, drain, and source.
yeah. And on the receiver side, the after the small black triangle, there is a big white triangle. What is that?
I'm not sure. The website I lifted this from, they didn't go into very high detail of the circuit elements. So, yeah,
It just specifies that basically you're only sending current one way. If I remember correctly.
Yeah, it's
rectifier.
operational amplifier that includes much more elementary units.
So it's like a photomultiplier.
Well, it's more for increasing amplitude of electric signal.
Yeah.
Yeah, sort of interrupting. That's for that.
And so that's wireless communication, but for a lot of applications, like it's more efficient to communicate through like a fiber optic wire than wireless transmission because I guess it's easier to send some, or you get more scattering through air than through like solid state. So this is just a figure of like the loss of a signal depending on the emission frequency of what you're trying to send through. So this axis is micrometers, and you usually get two types of scattering. You either have your fiber optic, it either absorbs some of the signal as it goes through the waveguide, or it gets scattered by impurities inside the waveguide. And then people have done measurements, and then there's optimal transmission frequencies for any sort of cable that you're trying to do. So if you're trying to send signal with low losses, you want to kind of optimize or reliably have send signal within that range. So you can have optimal communication between two things. Like if you're doing a supercomputer calculations and it submits it to a bunch of different nodes, you don't want to lose information between nodes.
So micrometer is like 1,000 nanometers.
Right. Mm-hmm. So this would be like mid IR. If I go back to or short IR.
What is decimeter per kilometer?
So decibel is, I'm assuming, just like the strength of the signal, and then the kilometer is like how long it travels through the wire.
But is it decibel normally with sound? I don't know.
I didn't hear your question.
What's the nature of
So
that
why
decibel
is the units decibels per kilometer? Because I've only seen decibels in sound. So I don't know if it's,
It's intensity of light and intensity of sound. You can both, I think, measure in decibels.
Intensity of.
What was
Does it just
decibel?
measure
Like,
like intensity of waves in general, I
Yeah.
guess, or like?
yeah.
Is it linear or logarithmic?
it's
scale?
logarithmic.
Yeah.
So it's you divide by some reference point and then measure how many times it is stronger.
Yeah, in
Take
sound
over.
is 120.
But if it would be general audience, maybe one may find in Wikipedia like changing by 1 decibel, meaning signal becomes like 10 times weaker.
Mm-hmm.
Just for comparison. like 10% weak or whatever.
Right.
So it's the minimum of that curve is at in the infrared.
Right, it's at like 1.6 micrometer. And so when I was looking up, because, well, I'm presenting on new materials for IR emission and sensors, so it would make sense to kind of go back and through and categorize what are like conventional materials used now or materials that are used now. And I looked at this from the book I found here. And I guess there is a variety of ways that people have tried to get band gaps with the right IR emission. But I guess the one I really looked into was, or the standard that a lot of technologies use, is the mercury cadmium telluride. Is because I think it's mercury telluride has a 0 band gap, or it's a semi-metal. And so if you dope it with small amounts of the cadmium, you can tune it in between 0 and half EV. So you can kind of get efficient IR emission that way. So that's kind of like, from what the reading, a little bit of reading I've done anyway. Right now, cadmium, or mercury cadmium telluride, is kind of like the standard or the most efficient material used. And then, yeah, everything that all these materials would have in common is, if you consider like a band structure, the energy spacing between the emitting or the absorption peaks for IR, it's like you have to have the right energy gap, which corresponds to roughly 1 to 10 micrometer range. And you also want the radiative and the non-radiative relaxation between those two states to be roughly the same order of magnitude if you're looking for efficient absorption or radiation.
Why do you need that for efficient emissions?
I didn't put it in here, but for emission, PL quantum, which is like a measure of how efficient it is, it's KR over KR plus NR. So if they're roughly about the same, you're going to get like 50% luminescence quantum yields. So you want them to be like on roughly the same order of magnitude at least. Ideally, you would want the radiative rate to be orders of magnitude faster than the non-radiative.
Is that like physically unrealizable for whatever reason? I mean, is it just not realistic to basically minimize the non-radiative relaxation?
It's hard with wider band gaps. You can get quantum yields near 100, but I think because since you're talking about IR emission, it's like the energy gaps are so small, they're like on the scale of like thermal fluctuation. Yeah. That's kind of hard to suppress like thermal excitations and de-excitations within that range. Yeah, I suppose. Because I think mercury, cadmium telluride, from the reading, I think it's one of the most efficient. It gets like 50 to 60% quantum yields. So yeah. And so I mentioned this because for the results I'm going to be looking at, it's basically just comparing radiative and non-radiative path relaxation for the simulations we're doing. And so those are materials that have been used for IR emission. These are kind of state-of-the-art current research fields for nanoemitters. So we have collaborators or competitors here at NDSU who they work with people in Los Alamos, and they try to figure out how carbon nanotubes can emit photons or absorb photons in the IR emission. And this is from a recent Nature paper that came out of Los Alamos. You can see based on the chirality of the nanotube, so each panel corresponds to a different chirality of the nanotube. And I'm not sure which type of functionalization they used or what kind of dye they put onto the nanotube, but you can tune the emission from 1 micrometer, which is its lowest excitation, to like 1.4 micrometers. So you're still in the near IR range within that tunability anyway. So those are some recent results that have been found for IR emitters. And then I just came across this paper. Matt Beard, who was here last semester, who gave a talk for MNT, he just came out with a review paper on or quantum dots that are kind of used for IR or near IR emission. And so each white bar corresponds to a certain material, and then the range of it corresponds to the tunability of the wavelengths. Because with quantum dots, just by changing the size, you can change the band gap. And so like I was talking about before, the mercury telluride, you can kind of tune it in between the mid-IR and single IR, and it has the kind of the widest breadth for tunability. And near the bottom, we can see that perovskites are kind of starting to make it on this list now too. And I circled that one because that's the material that we're going to be focusing on for our simulations. And so there has been a challenge in trying to extend the emission of perovskite nanoparticles out to the near IR or further into the IR. So this was the first reported paper for the perovskite nanoparticle or quantum dots. And you can see you can tune the emission all the way from 400 to a little less than 700 nanometers. But the cesium lead iodine structure is relatively unstable due to, it has to do with basically geometry and filling factors. So basically it just has a low crystal stability at room temperatures, so they degrade. And work that the same group did is just substituting the cesium with larger cations. They found it made the structure more stable, and for some reason, I couldn't remember exactly why, but they also see a redshift in their quantum dots too. So here it was below 700, and just by changing some of the chemical composition, they were able to extend it out to 750, which is at the very edge of the near IR. So the work we want to do is going further than that. Well, there's supposed to be a little arrow here indicating how far we can go. And just doing some literature search, one way I found that people have tried to extend out further into the region is using dopants, or putting dopants into the nanocrystals. So they found that if you dope the cesium ones with the wide band gap with rare earth metals, I think they used urbidium. They found that they were able to, ytterbium, is that how you pronounce it? I don't know, I've seen the words, but I've never actually had to say it. Ytterbium. Well, basically the group, they just focus on doping materials and then trying to figure out cool things they can do with them. So they found that if you excite the nanoparticle, that it transfers, somehow, it's not really known yet, but it transfers energy to two the urbidium states, which are within the band gap. So you essentially get multi-exciton generation, where if you excite one, the perovskite, it gives its energy to two urbidiums, which have a band gap, which is roughly in the 1,000 nanometer.
So this is like single fission. Single fission.
Multi-exciton generation process. This converts one high energy carrier to two small energy.
So are they singlet states or triplet states?
Theory says they're triplets.
So it is.
And I'm not sure
So
what the
this is-
state of the urbidium
Terbium
is.
is excited. Terbium is triplet.
My D-metal chemistry is not, I'm not very familiar.
No, it's not like background. It is just to check because those rare earths can go to crazy high values of speed
Mhm.
degeneracy. It can be like 9 halves or 11 halves easier. It's not necessarily true.
I meant the perovskite exciton is. Or that's what the theory says anyway. So this state would be a triplet, and then how it converts this high energy,
Then it goes back to singlets.
possibly. The process isn't really known yet because this paper came out like last summer. So there's still, like I saw one paper, they were trying to do atomistic modeling to see if they can get states within the band gap, but they didn't find any states in the band gap, so the mechanism is still not really understood, aside from the fact that you do see greater than 100% quantum yields for the IR emission. So that's one way that people have kind of figured out how to get IR emission from these quantum dots. And then what we're focusing on is whether we can use polarons that form in these nanocrystals to get IR emission in these states. And so I didn't put a lot of information in Polaron, like the ideas of Polaron background, because I did that in my last talk. But I guess the basic idea is, if you look at this paper, so if you you have a neutral state, then you photoexcite it. You have positive and negative charge that are in your lattice now. And since perovskites are ionic, they interact with those excess charges now, and then they move around. Just kind of screen the charge. So you can kind of see here, you put an electron here, it pushes the negative charges away, and it draws positive ones towards it. And then vice versa, if it was a hole, it would do the opposite. And then that's basically the idea behind a polaron. And then what that does is it kind of stabilizes that particle and makes it more robust. That's probably a bad word. It's not very physical. Basically, you get charges that localize in space, and then they become resistant against phonons scattering off phonons in the lattice. So they have extended lifetimes. And it slows down charge carrier recombination too. And so the idea that, well, I guess Dimitri came up with the NACS talk is if you look at these energy spacings so this represents the polaron energy spectrum. And so this is like the ground state polaron. This would be like the first excited state polaron. So potentially this energy difference here could correspond to about the IR, our energy need for IR emission or transmission. And then the paper I took this from, they were looking for a polaron absorption in these materials, and they found that, well, they saw polaron absorption in these materials at different temperatures, which is beside the point what I'm talking about here. So basically they did see signatures of infrared absorption due to polaron, which they attribute to polaron formation. Yeah, Tian.
Can you move on to the previous slide?
Mm-hmm.
So the depth of these wells is like the strength of the polaron.
Mm-hmm.
So you could, if you engineer the material where you excite and the atoms don't do anything, then that's a very weak polaron effect, right?
Right. So
these wells will be shallow. Is that that the right way to think about it?
If you had no movement, it would be like a small.
Okay. So the depth of these wells is like the polaronic effect, the strength of the polaronic effect.
Mm-hmm.
Or,
Yeah, so I know people have done like solutions for perturbation theory on these. I think they find that like the self energy of the polaron is coupling parameter times h bar. So this is the phonon mode that it couples with. And then alpha, I forget the exact.
okay, but it depends on the strength of that coupling with that phonon mode.
Right, and that's what alpha characterizes.
So the strong, yeah, okay, so these wells are like, the deeper they are, the bigger coupling you have between the charge and those phonons, certain phonon modes.
Mm-hmm.
So this is all, depends on the type of atoms you have in the lattice.
Right, it's material dependent.
It's material, yeah, very material dependent.
Mhm.
Not so much like nanoparticle size.
As long as it's big enough, or it's like, as long as it's bigger than the polaron that forms. Because otherwise you get like a quantized polaron, which is, I'm not sure what the physics would be behind that. But.
Okay.
And these materials, well, this paper, they suspected that the polarons are like kind of the size of 9 nanometers. So it's a large polaron. So it's smaller coupling. I think I've seen some papers that calculate that like this alpha parameter is like 1, it varies from like 1 to 2 for these materials, which would be a large polaron formation.
I do not have a question. I just I'm always pleased to hear about hydrogenic model.
Mm-hmm.
Is it related here?
Yeah, I guess as an approximation to like the energy spectrum within the well, like a first approximation, you could just do like a mean field, like the same idea behind like Coulomb binding, or like the Coulomb's or exciton spectrum.
So the potential is created by distortions of lattice, and the charge carrier can be excited through these quantized levels, and this quantized level, of course, distortions of lattice is stronger near the center of Polaron and decreases to zero as one goes apart. And this approximately goes as 1 over r. It creates effective potential similar to pi division.
Yeah, so it's like you have a negative charge and a mean field around it. And so the easiest way would just be to take the average charge as a first approximation. And so that's why the spectrum kind of looks like something similar to a hydrogen atom. So like this first energy difference is large, and then the spacing gets denser the higher you go up in the spectrum. And I guess for pretty much all the models, they're approximate. There's no exact solution. So it's, for every single case, you kind of have to come up with a new argument. So, yeah, this just shows there is Polaron formation in these perovskites. And the axis they use is wave numbers, but I think this transition 1200 wave numbers is like 8,000 nanometers, so 8 micrometers.
What does it mean TRIR?
Time resolved IR spectra. So I think it's like a pump probe.
So the pump is visible.
Right. So they create the Polaron.
It will not, this perovskite structure will not absorb in the near IR if it is not excited preliminary with optical.
You have to form the Polaron first,
Okay.
and then probe it.
So, when we talk about Polarons, do you have to always take excitonic effects into account? Does it go hand in hand? The electron attracts the hole, but the motion of the atoms around them screens this interaction.
Right.
So
So it's
it diminishes the excitonic effects.
right. Yeah. So you can see that since you have two different charges, they're gonna interact with the mean field differently. So like this is going to go to the bottom of one electron's going to go to like where it's more positive, and then the hole is going to go where it's more negative.
Right.
And that's what this picture kind of illustrates. If this is your spatial coordinate, you're going to have localization, and they're going to be in different regions of space.
So you can't talk about Polarons without excitons.
I see what you're saying. So
Like excitons screened by atomic.
so it splits the
So it's well,
Can I? Please correct me if I'm wrong. So, in the perovskite community, people believe that excitonic effects are very small and negligible because the electric constant is around 1000. Okay. First. Second, Polarons can be created as Aaron introduces by optical excitation, but it's not necessarily that positive and negative Polaron exist simultaneously. You can inject charge and create separately only negative or only positive Polaron.
oh, okay.
So Polarons exist even without
Conservation of charge.
without optical excitation.
But I thought Polarons were like the reorganization of the ions in space that like traps the charge, right?
Yes.
So,
So this bluish and reddish potentials are like traps where
yeah.
charge creates distortions and then it gets trapped in its own distortions.
So on the next slide, you show spectrum, whatever, with different temperatures. Is it known if there's like an ideal temperature, or is it hotter the better, colder the better, or is it like not as good and then you heat it up some and it gets better, heat it up some more and it gets worse?
I think the higher the temperature, the more Polaron formation it is.
But then wouldn't that contradict the lattice, because then the lattice has more vibrational energy, so then it can, by chance, get away from where you have dipoles forcing charges into one location?
Maybe there's an inversion point. At some point, maybe this would go down, but well, I guess the physical constraint is it has a pretty low melting point.
Oh,
So it's like it can only go up to like 400K maybe 450. But I think, well, the reason that it increases with increasing temperature is it activates vibrational modes, so that methyl ammonia, like for the perovskite, and the activation of those creates the Polaron. So that's why at lower temperatures it doesn't form. Well, at higher temperatures, that the vibrational modes it has the energy to move with the charge.
and then if you get too hot, it just melts.
Right. So yeah, this is kind of the end of my presentation. So then, yeah, we're going to use a model we've used previously, the perovskite quantum dot, to model Polaron formation in these materials. And one of the reasons that we use the quantum dot, or like this cluster, is because if you use periodic, like if you want to do like a thin film or a nanowire or a bolt, the problem with that is you have to use periodic boundary conditions. But since when you put in an extra charge, it deforms the lattice, it's like it could potentially screw up the boundary conditions and you'd have to play with that a lot. So it's easier just to use a cluster and just a lot of vacuum to try to look at Polaron formation.
So is your system large enough that the ligands won't influence the polar formation?
Probably not. But I guess I've looked at other papers like Sergey. He basically just uses the same 2x2x2 crystal structure when they're looking at Polaron formation. So it's basically the same size of what everybody else is doing. So it's probably not optimal, but it's competitive. And so, yeah, just kind of overview a couple of ways we're going to try to quantify Polaron emission in these systems. And so this was the project we had some initial results for Ben, who was in Dimitri's PChem class. So over there you might have seen some of these results, but basically we want to do Wavepacket Dynamics for the Polaron ground state, and then the first or the lowest Polaron excited state. And then we parameterize it with DFT. So these potential energy curves come from DFT calculations, where first we do just a Polaron ground state geometry optimization, which is this point. And then we just do the lowest excitation in DFT, and then optimize that structure. And then with the same electronic structure, we just use the ground state geometry to get this point. Because since this is the reaction coordinate, it's the same geometries. And then we just do the reverse for the ground state. So we do excited state geometry with ground state electronic structure. And that's how I made these parabolas for the potential energy surfaces. And then I did two sets, one for singlet spin configuration and one for a triplet, just to have a reference for when doing these calculations. Then what I found is that the triplet, the change of geometry is lower compared to the singlet.
What is Polaron ground state?
So it's, go back. So like this state here, if that makes sense.
How do you calculate that ground state? So you optimize your geometry without any Polarons, and then
And then you just add a charge
okay.
through like constrained DFT. So you optimize it with just an extra electron or one less electron.
You define where that electron is spatially, or you like throw it into a particular orbital that you know kind of lies in some region? I guess I'm confused about how that, constraint would actually work.
It's a keyword +1.
Or
Is
is it
DFT the Gaussian or positive?
Do you say this lead gets an extra electron?
I let DFT or I let VASP do the thinking. So I just tell it, so if my ground state's 100 electrons, I just tell it do 101 electrons.
So
Oh, okay,
it's
so you're
not
just literally throwing in an extra
DFT.
electron in.
Right.
Just let it do its thing.
Is it constrained DFT? Because I thought constrained DFT, you tell the program, this is the electronic structure I want, which would mean that lead has an extra, this specific lead has an extra electron, and you demand that the density recovers that specific electronic structure.
It's not literally constrained DFT, but it is a constrained onto DFT.
Yeah, that's what I meant by constrained DFT. So it computes the orbitals essentially, and then it just,
You just add another electron.
right, and then whatever the orbital it calculated before, it's pretty close to that, just changed a little bit. Which we'll see later for geometry optimization. There's not a lot of change between the Polaron and the ground state.
It treats what used to be
And unoccupied.
LUMO as now occupied.
Right.
In
I
calculation
I
of
understand
the
that,
Constant.
but I was, when he said constrained DFT, my brain went to, you are imposing that this lead or this atom has an extra electron, not give it to the entire system, whoever is the strongest will take it and win.
Whenever I hear constrained DFT, I just think of the parameters in VASP. That's what I always assumed constrained DFT meant, but I'm probably wrong. I haven't done much reading on it. So, yeah, so that's, oh yeah, we were back here. So yeah, that's how we constructed the potential energy surfaces. So basically just put it in an extra charge, geometry optimize it, and then that defines the reaction coordinate.
So based on this diagram, if one starts at blue potential at 0 at minimum, promote to the orange, right up, and then it will relax. As soon as it reaches the minimum of the orange, it will be able to emit all frequencies coming to 0.
Say that again. Or maybe draw it.
Well, I'm just checking if I understand what you mean in the right way. So if you excite from here to there, then it goes back relaxing, and then it is able to emit at original frequencies, at lower frequency, lower, and then at 0 frequency.
Yes.
And then it has ability to be like excited to the ground state. But it will not. Probably it will just recombine non-radiative. Is it what it shows?
As far as I understand the MATLAB code anyway.
So this potentials suggest that it will not emit or non-radiative channel is more preferred.
Yeah, and that's kind of what Ben's initial study showed. I think he found a maximum of like 7% efficiency, and it was at very low temperatures. So yeah, this second part, you just essentially initialize your nuclear wave packet, and then let it oscillate along the curves, and then it decides to decay radiatively or non-radiatively. And then these are just the Marcus rate equations for that decide whether it's non-radiative relaxation or radiative relaxation. And basically the only difference is the coupling terms, whether it's non-adiabatic coupling or through oscillator strings.
What goes in a triplet state calculation? Just real quick, how do you do that?
You can tell DFT which, like, the number of spin ups and spin downs that you want.
Okay.
So that's the rough way to do spin multiplicity, anyway.
It misses degeneracy and quality references, but it keeps one of the triplets.
So, those are describing Wavepacket Dynamics, and then since we've covered like our methodology a lot, I didn't go very far into it, but basically for ground state optimization, we've done 6 models so far that we're looking into, and I have results for 2 of them at the moment for excited state dynamics. So both positive polarons, so it has an extra hole in it, and then for the singlet and doublet configurations. And then to determine quantum yields, we just use oscillator strengths and the Redfield tensor elements. And the reason I do summations is because the ground state is twofold degenerate. So you have 4 possible relaxation pathways. So you just have to take them all into consideration for the yield calculation. So results for structure calculations. So this is just an image from MATLAB. So this is the quantum dot, which here is the lattice, and then the ligands on the outside. And then these iso surfaces, they represent par charges, or orbitals. And this represents adding, if you add a negative charge into the system where they're localized. And then these arrows represent the directions that the atoms move in response to that additional charge. So the structure represents the ground state, and then the arrows represent where the ions move for the polaron formation. And then the arrows are just over dramatized to illustrate which way they're going.
So the arrows are multiplied by factor 10 or factor 100 or whatever.
Mm-hmm.
It's not that atoms move by the length of the arrow.
Mm-hmm. It's good comparison just relative to which atoms move. This one shows the cesium, or the middle cation, where those ones move, and then this figure shows where the lead move in response to the extra charge that's in the lattice.
So in comparison to Wikipedia general knowledge image, where positive and negative go inside, inward and outward, it shows also like circular motion, and maybe going to from cubic cell to something less symmetric.
Mm-hmm. Yeah, I guess. Yeah, I haven't done an analysis of like the crystal structure itself. I've done bond lengths, but not whether it's the crystal itself transforms. Well, I guess there's small rotations.
But they're not definitely not going consistently inward and outward. It's more complicated configuration.
Oh, for each single ion motion, yeah. So like you can see these ones kind of make sense. You have a heavy density of charge in the center, so these ions move towards, or this is negative, these ions are positive, so they move towards it. But I don't really understand why these ones are moving away. It could be in response to these ones moving towards it.
Yep, it can create strain and
Right.
Is this like is there like some loss of information in the length of those vectors because you're going from 3D to 2D? Like some of them can be pointing
Yeah.
at you,
So yeah, it
and
is a
they look
projection.
this short, but they're actually as tall, as big as the ones that are perpendicular to the field of vision. You know.
That's a good point. Yeah. So the image doesn't give you all the information, but I've done some statistical measures to kind of quantify the movement of these ions.
Also, is the multiplication factor on the arrows the same in both for cesium and lead, or
I think I tried to make them the same.
because isn't cesium much heavier than lead
Mm-hmm.
as an atom?
No, let's have. Lead's heavier.
Cesium's
Lead's
pretty
82.
far down.
I think lead has an atomic number of 82. And then cesium's 55.
Yeah, I think it was a row down and then
Yeah.
a little bit over.
But I mean, they're both pretty heavy though, so it's
Oh,
going to
I
take a
must
lot of
think
charge.
so. I remember.
Yeah,
Maybe
but the-
like 8.
And for stable configurations, inertia doesn't matter. Even if it's like heavy.
Yeah, it's 55 for cesium and 82 for lead.
Forces.
Forces.
So it's almost twice as heavy. I realized it, but almost.
Yeah. It seems like
Mhm.
a transition.
So those,
Yeah. We'll see eventually the leads don't move as much compared to the cesium and the bromine.
No,
displacements. They are displacements.
But
Displacements
doesn't,
of
is
comparison.
this normal mode or what is this again?
So, so the structure you see, that's the ground state geometry. And then the arrows show where those ions move in response to putting a charge in. So these arrows show
So
where,
it's not like a normal mode.
right, it's not normal mode, it's just an illustration that you put in a charge, there's geometry. Yeah. So it's not very helpful for like very in-depth physics, but it's just a nice picture to look at.
So where does the polaron form on the right side, left side, if there is one?
I guess everywhere, since it's such a small cube. I guess it's hard to identify like where the polaron begins and ends. But I guess the best way to characterize it is just comparing bond distances and bond angles between the ground and
Right,
inside.
the ground state density difference? Because if,
Not familiar.
so if you made like a cube of the density with an extra electron without the extra electron, so the difference, that will show you where the electron is. And then that should be where your polaron has some locality. Otherwise, if you don't have localized electron, then you're not really forming a polaron. Right?
Case, we would be not limited by computational resources. One may want to try to increase size of this with a hole that take a bit larger, substantial change in difference that you're talking about, or charge distribution frontier orbital, which in some point is the same. It localized in the center.
But due to the size, it's kind of all.
Yeah, it's hard to describe. I know I've seen one video from one paper, whereas I can't remember which methods they used, but they basically showed like the region where the polaron was within their atomistic model. And I assume one way you could do it is just doing like dot products of like vectors between ground state and excited state. Because if you assume that it's like a continuous change in geometry, you get to a certain point where the vectors are basically the same after you add in some structure. So you get a dot product of 1.
Would it be 0? Because if you have a point where it changes a lot, that product would go to 0. Where
Right.
it doesn't change, then it's.
Then it would be 1. So then that way you can define
Yeah.
within your model where the polaron is based on some sort of criteria. So that'd be one way to try to illustrate it. So yeah, that was just a figure to show polaron formation in these systems. And then I tried a couple different ways to characterize structure. So a common way to do it for structural characterization is just radial distribution functions, or pair distribution functions. So basically you just measure bond distances, you bin them throughout the entire model, where R is just your variable and these are the bond distances between two atoms. And so I've only done this PDF.
We can just lay on the desk something.
Yeah.
Or the PDFs or printouts shouldn't have this reach.
But you can still kind of see the points. So this is for the positive polaron. So you put it in an extra positive charge. And this figure's for cesium bromine distances, and this one's for lead bromine pair distances. And for this figure, you can see black is the ground state, so that's the reference, and then the red and green dot are single and triplet states. So you can see for the closest bonds, anyway, you get bond contraction, or the bonds become shorter, so it's because there's more of them within this region. So it indicates that there's some bond contractions here. And then same with the lead bromine pairwise distances.
In this offset of dashed lines comparing to solid line decreases with distance. For smaller interatomic distance, the green and red substantially differ from black, and as we go outwards, it decreases.
Right, so that's like it.
So just the effect that you guys are looking for. Okay. So if it would be larger displacements away from the center.
Oh, these would be, so this would be increased too.
No, if it would be not Polaron but some like crazy noise, the green and black or red and black curves would have substantial difference at larger interatomic distances. But the curves kind of converge. They have some difference at lower values of argument, and then they stop to change from each other.
Yeah, those are the two I did for the positive. I haven't done it for the negative yet, so that's something I'm playing on.
So for the cesium, it's not in the center, which is why the lead has two peaks at like 3 and 4 and 4, right? Or why is there 2 peaks in lead and 1 major peak in cesium?
I guess we can look at the picture, try to figure it out. So cesium's in the middle, so it's basically just a radial distance.
Which color is cesium?
Cesium's the blue, the light blue. It's kind of hard to see. Then lead is the tan. So with cesium, everything can be a radial distance. And lead, it's like you have the closest pair,
So
and then you also have across the cell.
Does it show any asymmetricness of your lattice?
You mean a radial distribution function? What shows it?
Oh wait, no, never mind. Never mind.
So we're good on radial distributions. So yeah, negative Polaron to be determined. And then a more statistical method that Dimitri suggested is root mean square. So basically if you have a reference number that you can always do a root mean square. And basically root mean square is just you take the difference of whatever you're trying to measure and square it. So you cancel out the negative amplitudes and then normalize it to the number of things you're measuring and then do square root. And so in this case, dx, dy, dz is just the difference in x, y, and z components for the same bond for the ground state and polaron. Mm-hmm.
If cesium is in the center of the cube, how does cesium move closer to bromine? How can you move closer to all bromines at the same time?
Relativity may make all bromines.
All bromines. Okay, so it's bromines move closer to cesium.
Yeah, that might be a better way.
In just that region where the polaron kind of is.
guess I'd have to think of a better way to explain it.
No, this cube shrinks where the Polaron is. That's how
Yeah, I guess
all
you
of
could
them,
think.
because all of them have to come closer to the cesium. It's in the center of the cube, right?
Mhm. I guess that's one way to look at it. I guess, just to jump around a little bit for what you're talking about. So I didn't put the bromine ones on here because there's a lot of air, like there's 54 of them, so the image gets kind of dusty. I can't remember, but it seemed like for a lot
on
of,
the edges of the cube.
yeah, so all these red ones.
And the cesium is in the center of the cube.
I noticed for one of the models, when I was just going through, it seemed like a lot of the bromines, they were radially pushed out. I guess I didn't think about it much at the time, but it could be due
That
to,
increase the light.
right. So I guess I would have to look more in depth to see whether there's a way to take the information from this picture and compare it to the radial distributions. I mean, it's all kind of hard because it's kind of qualitative. It's kind of hard to do it numerically.
Or could it be an effect that you're working with a like small structure and everything kind of gets pushed together?
I mean, they're known for being like a soft material, and then the ions, they're ionic conductors. So like in real life, that you usually have ions that diffuse through the lattice as well too. So that's another complication. So they have a lot of movement variability within the cells. So, where was I? Okay, so root, mean, square, and then this is just a bunch of tables, the calculations. And I decided to do it, the root, mean, square just for each atomic element, because since it's normalized for number, like if you did them all, like it would just kind of wash out any meaningful data. So the ones I'm going to focus on mostly are bromine, lead, and cesium. You can see for the positive polarons anyway, there's a consistent trend where with increasing spin multiplicity, there's more deviation of the bromine bond for the positive polaron. You could kind of correlate that to you have positive charge, the bromine's negative, so with increased multiplicity, they move a little bit closer, or they contract inward a little bit more. That's one hypothesis anyway. And cesium, there's no real trend, there's not a lot of movement. One thing I just thought of now, for singlet and triplet, it requires putting in two, or having two charges, but the doublet is only one. So that might be why this one shows a difference, because maybe a singlet and triplet, the charges wash out. So that's maybe why the doublet shows a different trend there. And then for the lead, there's not a lot of difference between the bond distances. And for the negative polaron, there wasn't a lot of change in the data either based on spin multiplicity. So they're numbers, but they don't really tell you much. But they're good for supplemental information. Mm-hmm.
As part of the equation, is this function sign inside the square root?
Nope, it's on the outside. I guess the summation is just for summing over all possible bonds.
No, so
Some of all of this
it
function.
should be number of atoms. Because in root mean squared deviation, you do not care about where, you only care about where an atom is, not the adjacent neighbors. So if you don't do it correctly,
Right.
then you get crap.
Yeah, so the dx is different in, yeah, you're right. It's different in the atom positions
Yeah.
for x, y, and z.
So you have your reference, which is whatever, and then you have what you're comparing it to. You take the difference in positions.
Right. Yep. Yeah, the sum is just overall atoms then. And then another thing I tried is doing vector projections. So this is what I meant by, so this would use the bond analogy. So you could imagine that, like, if this was your bond in space for your ground state, and then if you add in a charge that it changes by a little bit, you could do the dot product of those two vectors and try to gain some meaningful information about change in geometry. And so I did that, but then I couldn't think of a good way to present it because all the changes were less than like 1%. Or if you normalize it so that your dot product is 1, it's like all the dot products were like 0.997. So it's a very small change. So it'd be hard to present it and gain meaningful information out of it. So it's something I tried, but something to think about, or potentially. But the one thing I realized when I was writing this out is if I just change the equations a little bit, I could solve for bond angles, and that might be more reliable, or it might be a better way to describe Polaron formation. Change in bond angles, some of them.
Dot product is nearly close to 1. Wouldn't your angles not change much?
True, but some of them might change a little bit more. Yeah, it might not be helpful either, but something I thought about anyway. So, move on from this. And so, I calculated optical spectra for 6 models I presented earlier. So, positive, negative Polarons with different spin multiplicities. And so, this first panel is sideways. Just rotate them real quick. But the main takeaway is that the positive and negative, oh, it cut them off too. Okay, sucks. Positive and negative Polarons give bright IR transitions, while the doublet is much less so. It's kind of a mangled figure. But so, single and triplet, and then the important information is that the lowest energy excitation, it's on the order of about 0.1 eV, 0.05 eV. And that corresponds to about 20 micrometers for IR transmission, so it's in the, I think, far IR from earlier. So it's a little further than technology applications, but it's still pretty close to the mark anyway for the lowest optical transition. We see that's pretty bright. So for the triplet, you get 2 that have pretty moderate oscillator strengths for that transition, and same deal for the positive. Whereas in the singlet, you have some small IR contributions, but you also still have a bright exciton transition, or what you normally see go across the band gap. And the negative Polarons picture is a little bit better. They all show pretty bright IR transitions, and then the energy gap's a little wider for the negative Polarons, and it's on, it's like 0.18, 0.2 EV, and that corresponds to about 6 nanometer IR, so that's like mid IR. And that's kind of even value over the conventional materials I talked about earlier. I don't even, maybe one of them got out into that region. And they all have pretty bright oscillator strings for those transitions. Or they're at least all above 0.1 in the 0.1 to 1 region. And single and triple, you don't see exciton, a photoluminescent or oscillator strings, that gets quenched. But in the double, you still see potential for the across the band gap emission. So that kind of indicates for, if you want to completely quench visible light excitation, you have to put in 2 charges, or take out 2 charges to get the IR emission. Because the double, you just put in 1 or take 1 charge out. So the optical spectra gives good suggestions, or positive, a potentially positive result that efficient IR emission might be possible in the regions that we want. So this is just some preliminary excited state dynamics calculations. And I mentioned them earlier, but I'll say it again. We only have it for 2 models so far, the positive singlet Polaron and the positive doublet Polaron. And the left shows like our conventional green figures that we do to show carrier cooling in these systems. And I'm going to have to work it out a little bit because it seems, since we're changing with the occupations, the code has to be, well, what I think has to happen is the code has to change a little bit because it.
Question. Why do you excite electron if you're studying positive Polaron? So this Polaron was like, please correct me. The idea is that standalone positive Polaron is created by injecting positive charge. And before you do infrared absorption, it like follows Fermi distribution, thermal. It goes like original HOMO is empty, and original HOMO -1 is populated, and then like what was the reason to excite an electron? Why don't you put it like no electronic excitation from the first second?
I guess I could do that too, but I guess I was just trying to compare cooling rates, if that was possible for the electron. But then I realized that
The cooling rates are only for holes, right?
the reported ones, yeah, are the ones
Yes.
here. So I guess in the physical model, like we're following that we're just taking, or we're putting in 2 positive charges, and then we wouldn't have to consider electron relaxation. But I guess when I was doing this, I'm just used to the mode.
Okay.
I was in work mode, trying to get data. So.
Okay.
But yeah, the other option I had was just like, you could just ignore the figures that don't work and focus on the holes, since that's what we're interested in anyway.
So one can make zoom in to the energy range corresponding to dynamics of positive polar, like from -2 to -1.
Mm-hmm. Yeah, that'd be the easiest way to circumvent it. Then, yeah, I did do a comparison of hole cooling rates as a function of excitation energy for these systems. And so that's this spot here. So the black line is if you excited the neutral state, or hole cooling in the neutral atom anyway. And then red and green correspond to singlet and triplet for the Polarons. And the trends are pretty similar, but you can see that all of them have some sort of region where it looks partially linear initially, as a dip, and then linearly increases again. So they all show that feature, but they're just at different rates. Where the triplet rate shows the fastest relaxation in these systems. And so we're not really worried about cooling rates though, because we want just efficient radiative and non-radiative relaxation. So these are just tables plugging in, are showing the states we're considering oscillator strengths between these transitions, and then the associated radiative and non-radiative relaxations.
Can you go one step back?
Mhm.
So the green and blue curves are above of the red curve. They're higher.
You mean black curve?
On the left, on the right side, there are three curves: ground state, and positive over and single trip. So the relaxation for Polarons is quicker than for ground state. It's the same for orbitals with the same symmetry. So Polaron doesn't slow down the relaxation.
Right.
It kind of enhances.
Right. It enhances the cooling anyway.
Okay, speeds up the pool.
Which I guess, if you wanted to rationalize it, you could say that Polarons break the symmetry of the crystal lattice more, so you have more overlapping orbitals, which would normally be orthogonal. So that could facilitate quicker relaxation. So yeah, radiative and non-radiative. And so I guess I'll focus on the singlet first. So these units are in, for the radiative, they came out to be on the scale of microseconds for the IR emission, whereas normally if you're looking at UV vis, those are normally on the nanosecond scale. And so these all fall within the range of about roughly 1 nanosecond. But the non-radiative cooling generally either fell into very, very fast, so this corresponds to 1 over picosecond relaxation, because this is in nanoseconds. So this is very fast relaxation for these three states. But there is one where the rates were sort of comparable. So this corresponds to like 10 microseconds, or on the scale of 10 to microseconds. So this transition here is actually sort of efficient. I think it came out to be about 6 or 7% if you divide 0.9 by 0.9 plus 27. So there was one possible relaxation pathway that could give efficient IR, but since the other three transitions are basically zero, it's like it just washes it out. So we get an overall yield of 0.
That's micro.
I think this would be 27 microseconds, or 1 over microseconds. Pretty sure.
Okay, yeah.
Yeah. And then for the doublet, there were none of the relaxation channels were very competitive. The radiative rate was on the scale of 1 over microseconds, whereas the cooling rate was 1 over picoseconds. So it's like 6 order magnitudes difference. So it's the non-radiative is a lot faster. So takeaway from this is positive polarons probably aren't very likely to have efficient IR for these systems. Well, at least based on these calculations anyway. So,
5-6 orders of magnitude just for a one transition in non-radiative.
yeah, I know. The big thing that changed with this is the energy difference. It scales, I think, with the square. So if you have very small energy differences, it kind of slows down your radiative transitions quite a bit. I don't know, I've been trying to think of mathematical model, be able to scale radiative and non-radiative rates based on energies transitions. But I haven't come up with a good model yet to kind of predict what would be good emitters and what wouldn't be, just based on energy differences and couplings or orbital overlaps, basically.
But just from one system, it's like radiative varies between like just these low energy transitions, 1 order of magnitude, and now radiative is just 5 or 6 orders of magnitude, just from HOMO -1 to LUM.
Mm-hmm.
Non-radiative, just for one transition, it's such a big, such a huge difference. 6 orders of magnitude, 5, so it's
Interesting to look deeper at. I will just go with technical question. So for notations, is it when you go from neutral system to like positive polaron, in some sense we redefine what is HOMO and HOMO. So you keep notations of the original neutral system, or you redefine assignment of orbitals each time as you charge the system.
Each time. So these orbitals correspond to this system. So this Polaron system. So
You redefine.
I redefine.
So what you call HOMO is former HOMO -1. What you call HOMO is former HOMO.
Mhm.
Okay. Yeah, maybe when it's not for like, big research, but not to lose the audience, a little table with visualization of diagrams which show that definition of HOMO and HOMO changes. What was HOMO in the neutral system now is HOMO because he removes one charge. So it can be very confusing to intuitively analyze this.
okay.
Okay.
Well, that'll make a big, yeah,
Okay.
that'll make a big difference.
I guess you're
That's
right.
like, it's not across the band gap anymore.
Right.
Okay.
Or it's across like the Polaron band gap. Which is, I guess, not really a band. It's more
But
just
it's not-
states.
It's not a gap. Yeah, it's not huge, but it's still concealed. Better to like into band or lose the meaning of a gap and into band.
Yeah, it's hard to communicate unless like you're talking with Polaron people who deal with this a lot.
Who knows? Maybe we all become polar due to your talks.
But yeah, I did find it interesting that the brightest optical transition did happen with the slowest non-radiative. I don't know if that was luck or what. I thought that was just kind of interesting. And so what's next? Start doing calculations for the Wavepacket Dynamics. Since we now have the potential energy surfaces, maybe try to recruit Ben. See if you'd be interested in continuing that work. And then just waiting for calculations for more of the negative Polaron systems. And yeah, that's it.
Okay, let's thank her. In your plans for the future, you do have negative Polaron, but both positive and negative look like injection, creation of Polarons by injecting positive and negative charge.
Mm-hmm.
Do you have far-going future plans for creating Polarons by photoexcitation, coexisting of positive and negative?
Yeah, I guess I didn't mention it, but that's what explorer neutral charge.
Okay.
Potential energy but not just for that, for excited state too. So it's, yeah, so now we're just looking at either positive or negative. But then another way to look at it is you photo excite the system, so electron and hole, and try to see the Polaron dynamics in that system. Because it will probably be a little different because the charge in the quantum dot is going to be changed since you have a positive and a negative, so the ions might move a little differently. Probably not much for our small model. But.
Paper is open for discussion, questions. We had some, but maybe. More questions, one. More questions, two. More questions, three. Okay, then thank everyone once again. Well, thank you much for attending and supporting this discussion. We are closing formal part of the meeting. But if there are things to discuss, what you want to do is half an hour before the next meeting scheduled for this week. Next time we have 3 presenters. Great. You do present?
Yeah, I'm scheduled to present next week, so.
In 5 questions, present. So it's right? Okay, yeah. So it will be shorter.
Yeah.
My calculation is not done.
Still, it's so much more pleasant and easier to ask nasty questions when something is not done. When everything is perfect, what can you ask? Okay, yeah. So I'll put us off record.